This is the first of two films about static electricity, electrostatics. We'll be looking at some important applications of electrostatics in commerce and industry and in everyday life. But first of all, let's look at some laboratory experiments which show us some basic principles of electrostatics. When this plastic rod is rubbed with a clean, dry paper tissue, it becomes electrically charged. In fact, it's negatively charged. We hang it up so that its weight just balances the weight of the thin wooden stick pivoted on a razor blade. Now let's rub another plastic rod, just like that one, with a clean tissue. It repels the first one, because each plastic rod has the same kind of charge. They're each negative, and like charges, repel. Now let's see what happens if we try the tissue. It attracts the rod because it has gained a positive charge. And unlike charges, positive and negative attract each other. What happens when we create static electricity in this way is that one body acquires a negative charge while the other becomes positive. We believe that tiny charged particles called electrons have passed from one body to the other, causing the bodies to become positively and negatively charged. All matter contains electrons. If we heat up a metal filament in a vacuum and connect it to the negative lead from a high-voltage supply, electrons stream off from it. They produce a spot of light on a fluorescent screen at the end. This is a collector into which we're going to steer the electrons. It's connected by this wire to the plate at the top of a gold leaf electroscope. Because the electrons are charged particles, they can be deflected by a magnet, and we can guide them into the collector. Their charge passes up the wire to the electroscope, causing the gold leaves to part, to diverge. Let's watch that again. When we rub an ebonite rod with fur, the rod becomes negatively charged. Hold it near the electroscope and look, the leaves move even further apart. The negatively charged rod seems to increase the effect caused by the electrons. But a glass rod, which becomes positively charged when rubbed with silk, causes the opposite effect. It cancels out the effect of the electrons, and the gold leaves collapse when it's held near. Let's recap. The electrons charge up the gold leaf, causing it to diverge. A negatively charged rod makes the leaves diverge even further. A positively charged rod causes them to collapse. So what is the charge on these electrons? The tiny particles present in everything and streaming off from this hot metal. Are they negatively charged or positively charged? Think it out. And if the plastic rod becomes negative and the tissue positive, which has gained and which has lost electrons when we rub them together? When something becomes electrostatically charged, it's always because it has either gained or lost electrons. Work out from the experiment you've just seen whether electrons are positive or negative. Then you'll understand what's happened whenever something has become positive or negative in some electrostatic process. Here's a demonstration of an electrostatic process you may have felt for yourself. When you rub the dry soles of your shoes on a dry nylon carpet, you create electrostatic charge, which can build up to a high voltage. This girl's connected up to a voltmeter, which reads in thousands of volts. The charge builds up on her and on the carpet. Here's how she's connected to the voltmeter. Nearly 4,000 volts. If she now touched, say, some metal object, she'd feel a short, sharp shock as the charge passed from her to Earth. Not dangerous, because the current would be very small. If she now stands still, the charge leaks away slowly and she feels nothing. Many of you must have experienced this sort of thing in warm, dry rooms when you walked across a synthetic carpet, then touched a door handle or something. It's one of the nuisances of static electricity in modern life. Here's something more important, more useful anyway. This is a sheet of plastic material. Let's pretend to write on it by rubbing it with a finger in a nylon glove. We don't see anything, of course. But we can use the negative static charge built up on the plastic to reveal what's been written. The box contains a mixture of red lead and sulfur. When they're shaken out, the two powders become electrostatically charged by friction as they rub against each other. The red lead positive, the sulfur negative. The positively charged red lead particles are attracted to the negative charge created when we rub the sheet with our finger. And the writing becomes visible. This is the basis of a very important method of copying documents and so forth in offices and other places. It's called xerography, and here's a modern machine in action. Let's see how it works. Here's a paper we want to copy. It's put in the copier, and a system of mirrors and lenses produces an image of the sheet on the most important part of the machine, which is here inside. Running around these three rollers, there's a continuous belt made of a very special material, as we'll see. Let's look at it, pulled out from the machine. Here it is. It can be given a positive electrostatic charge when it's running in the dark inside the copier. Suppose this is a part of the belt, looking down on it. The little pluses represent its positive charge. Let's concentrate on just this section of it. Here's something we want to copy, a large X on a white sheet of paper. Its image is reflected onto the belt. Now the belt is made of material which conducts electricity when light is cast onto it. The white portions of the paper reflect light onto the belt, and the charge leaks away through the belt from those areas, because they're now electrically conducting, leaving a positive charge in a pattern corresponding to the black portions of the original diagram. If the belt's now dusted with a negatively charged powder, this sticks to the positively charged area, like this. We've now got a copy of the original in black powder on the belt. We've got an image of the thing we're copying, which we can see. When this page is copied then, the white areas, such as these, reflect light onto the belt so that it loses its static charge in those areas. Most of the sheet, in fact, is white, so charge will disappear from the corresponding region of the belt. But where there are black letters or lines, these reflect no light onto the belt, and the belt keeps its positive charge. This is the part of the machine where the black powder, given a negative charge, sticks to the positively charged parts of the belt as it passes over the brushes. Here's some of the powder. It's actually coated onto tiny metal balls, from which it's smeared onto the belt and sticks only where there's positive charge. The belt then looks like this. You can see a reverse copy of our document traced in black powder sticking to the belt. The moving belt is made to press against a blank sheet of paper and transfer the powder to the paper. Here's the original and the copy. But this wouldn't be much good because the powder is easily rubbed off, as you can see. So in another part of the copier, the copies are heated, which makes the powder really stick to the paper. The belt goes round and round, being charged, receiving a reflection of the sheet we're copying, picking up powder, transferring this to paper, then going round again, so that a modern machine like this can go on and on making good copies at a tremendous speed. And it all depends, in the end, upon the principles of electrostatics. Now for a very different application of electrostatics. First, let's see a laboratory demonstration. These leads are used to apply a very high voltage across this apparatus. The outside of this metal chimney is earthed, while the positive lead from the high voltage unit is clipped to a terminal which connects with a couple of wires passing down the middle. The wires go down here, but you can't see them very clearly at this stage. When we switch on, we'll now have a big potential difference between the wall of the tube and the wires passing down the middle. Across here. Beneath the chimney, there's a hot plate. If we put some ammonium chloride on it, it sublimes off, and its white fumes pass up. And out at the top. Now let's switch on the high voltage unit and turn it up so that we're applying about 21,000 volts. The smoke stops. Although it's still passing in at the bottom, turn off the high voltage and the smoke emerges again. This is a model of an electrostatic precipitator, which can be used to cut down industrial smoke. Watch it again. The forces produced by the electrostatic charge applied to the central wires cause neutral atoms to lose electrons and become charged ions. These ions are repelled by the positively charged central wire towards the outside wall. But they tend to attach themselves as they do so to the tiny smoke particles and carry these to the outside, as you can see. So we've got a very convenient way of preventing smoke particles from getting out into the atmosphere. Electrostatic precipitators are used in many industries. Many electricity generating stations use them, like this huge coal-fired plant at Fiddler's Ferry in northwest England. The tall chimney is just a chimney. It's not itself the precipitator, as we'll see. Powdered coal is burned in the furnaces to produce heat to make steam for the turbo generators. We'll explore some modern power stations in another of these films, but just now, let's concentrate on what comes out of the furnaces. Heavy ash falls to the bottom. The finer ash and smoke particles are carried up through flues, and if it were allowed to escape into the air, this would cause great pollution. Big precipitators are used to prevent this. you can see the great tube taking furnace gases to a precipitator, which is like an enormous square box, inside which the waste gases pass between electrically charged plates, which collect the smoke particles. Automatic mallets strike these plates, causing the powder to fall off into a container at the bottom. The cleaned gases then pass along to the chimney stack and are discharged into the atmosphere. There's a long line of precipitators, as you can see, dealing with all the power station's furnaces. There are 8 coal-burning furnaces at this power station, and each has 2 precipitators. There's the stack, 650 feet high, which takes the clean gases which have passed through the precipitators. Here at the top of the stack, we find another important application of electrostatics, something you've probably all noticed on high buildings. Lightning conductors. Enormous electrostatic charges can build up in certain types of cloud, until the very high potential difference between cloud and earth causes the air's insulation to break down. We get a flash of lightning. Lightning conductors provide a safe path to earth for the tremendous energy of the flash, so that the building itself isn't struck and damaged. See how the lightning conductors at the top of this stack are very thoroughly connected to earth by thick copper strips, which are covered with a layer of lead to protect them from acid fumes coming out of the stack. The strips pass down the outside of the stack. Here's one of the points at which the conductors are led down to a copper grid firmly embedded underground. This is the outside of a laboratory at UMIST, where very high voltages can be created artificially, so that, for example, electrical insulators can be tested to see how they stand up to a high voltage. We went there, however, to see a demonstration of artificial lightning, to see how well a lightning conductor works. Using special arrangements of capacitors, which can be charged up with electricity, a potential of 2 million volts is being built up. It can be applied to this single spike of metal, pointing downwards. 3.5 meters below, there's another spike, our lightning conductor, securely connected to a metal grid in the ground beneath. Watch. A potential difference of 2 million volts across an air gap of 3.5 meters causes the air to become conducting, and the electrical energy strikes to earth. Have a look at what happens when we freeze the picture for a moment or so. A lightning conductor doing its job. A fine example of physics in action. In this second film about electrostatics, we'll be looking at more important applications, more examples of physics in action. First, a demonstration. Electrostatic charge can be built up by the friction of a liquid against a solid. This pump can pump paraffin around a closed circuit of piping. Here the paraffin passes over a nylon surface. These are actually nylon pan scrubs. From there it passes into a copper container. and it's then recirculated around the back to the pump again. We connect the copper container and a metal collar in contact with the paraffin just before the nylon to the voltmeter in the middle, then switch on. As it rushes over the nylon, the paraffin gains an electrostatic charge, which it transfers to the copper collecting vessel. A potential difference builds up. In a short time, there's a potential difference between the paraffin from the pump and the copper container of over 1.5 kilovolts, over 1,500 volts. If we now electrically connect the 2 points across which there is this potential difference, the potential drops to 0. What's the importance of this? Well, it's important wherever non-conducting and inflammable liquids like paraffin have to be pumped rapidly from one container to another. So it's important where, for example, aviation fuel is handled, as at airports. A light plane is to be refueled. Before any fuel is pumped from the tanker to the fuel tanks in the plane, a line of cable is run out. It's called a bonding line. It's attached to some clean metal part of the plane so that there's now electrical connection between plane and tanker. Now the fuel lines run out. Another cable connecting the nozzle with the plane. And fuel can be pumped aboard. It's necessary to pump the fuel rapidly, or the whole process would take a long time, especially with the big jets. This means that there's the possibility of electrical charge building up in the plane's fuel tank. If a spark occurred, the effect would be disastrous. From the demonstration you saw earlier, can you see how the bonding line stops this happening? The job's completed, quickly and safely. There's perhaps less chance of a spark causing an explosion on a wet day like this, but even so, this procedure's always followed at every airport. It's just the same with the big jets. Here's one being pushed into position for refueling. She'll take aboard much more fuel than that light plane. The bonding line again. And there's a special connection point on these big planes. When fuel gushes through the pipeline into the plane's tanks, there's always the risk of a big electrostatic charge building up. The bonding line prevents this. It's part of the safety procedures, as important on the ground where planes and inflammable fuel are handled as in the air. Physics applied to making air travel safer. Friction can be used deliberately to produce electrostatic charge in the laboratory. You've probably seen this kind of machine, a Van de Graaff generator, which can be used to demonstrate all kinds of electrostatic effects. For example, let's put these strands of silk fixed to a metal base on top of the machine. Now we'll start it up. the belt carries charge to the top, where it's spread out over the outside of the metal sphere. At the same time, the separate threads of silk become charged. They all get the same kind of charge, and if you remember that like charges repel each other, you'll understand why this happens. Now let's discharge the sphere by bringing near this smaller Earth sphere. A spark passes and the silk threads collapse. If everything's made very dry and it's run for long enough, the machine can build up a potential of thousands of volts, sufficient to spark across this air gap to the Earth's sphere. Let's take a look inside this Van de Graaff generator. We must switch it off and discharge it first, or we'll get an unpleasant shock. Inside the base, the continuous belt runs just above a metal wire spiral. This can be given an electrical charge, which it then sprays onto the belt so that it's carried upwards. Or you can just simply let the machine run in very dry conditions, and there's enough friction between the moving parts to create charge, which is carried upwards by the belt. Let's look at the top. Here there's a similar device. Charge brought up on the belt now passes from it to the wire spiral and spreads out over the surface of the sphere. Now this is a laboratory demonstration model capable of building up a charge of thousands of volts under good conditions. There are much bigger machines. Look at this belt of a Van de Graaff generator. And here's the machine it's used on. This one can produce a potential of 6 million volts, so high that it has to be run inside a tall metal tank. You can see the top of this tank being taken off. The tank's filled with a gas called sulfur hexafluoride, a very good insulator. In air, great sparks would discharge it before so high a potential could be built up. The belt runs inside these rings. Here's the top. Inside, it looks like this. It's more complicated than the small lab machine, but the principle's the same. Here's the top of the belt running over a big pulley, and charge brought up from below is taken off it by a strip of metal gauze, which rubs against it. You can see the gauze brushing against the belt. Here's the rest of the tank coming off, so that we can see the bottom of the machine. Looking up it, you get a good idea of its size. At the bottom, a gauze brushes charge onto the belt, so that it can be carried up to the top. What are such enormous machines used for? Here's a sectional diagram. There's the tank of sulfur hexafluoride gas with the moving belt inside it. The very high positive potential produced at the top is used to repel positive ions, charged atoms, of various elements down a tube, so that they reach the bottom travelling with a very high velocity. Here we are underneath the generator. Certain of those positive ions, travelling very fast, are steered around this corner by a big electromagnet. They pass along this horizontal tube, which will bring them to focus on a target of some kind at the end. The target's jiggled about mechanically. If the fast particles kept striking it in one place, it would melt, and water's used to cool it. Such experiments show how different metals, say, will behave inside nuclear reactors and so on, and they hope physicists understand the structure of the atom, what matter is made of, and why it behaves as it does. Bigger and even more powerful Van de Graaff generators are being designed and built using the principles of electrostatics to investigate the structure of matter and to provide engineers working in the nuclear industry with the sort of information they need as they develop their exciting new products and processes. Back to the laboratory for some more experiments in electrostatics. One terminal of this battery can be connected using this lead to a metal plate on the left there. The other terminal can be connected through a very sensitive galvanometer to the other plate. There's air, of course, between the two plates, which make up what's called a capacitor. Let's start with the two plates very close together, but not touching. If we connect them to the battery, the needle shows that a current flows, but fairly quickly dies away. The zero is at the center of the scale. Here's what happens. The capacitor's at the top and the battery at the bottom. When we connect the battery to the plates, it acts as an electron pump, pulling electrons off the right-hand plate and making it, therefore, positive, and pumping them onto the left-hand plate, which becomes negative. This process continues, the right-hand plate gaining a bigger and bigger positive charge, and the left-hand plate a bigger and bigger negative charge. This goes on until the potential difference across the plates of the capacitor equals the EMF of the battery. No more current flows, and we say that the capacitor's now fully charged. We now connect the two plates electrically by touching the two leads together. A current flows in the opposite direction from before and quickly dies away. Look at the diagram again. When we connect the two wires, electrons flow back from the left hand to the right hand plate. Current flows in the opposite direction from before until all the charge has gone from the plates. We call this discharging the capacitor. Watch it again. Now the capacitor's fully charged and the current stops. Connect the plates and the current flows in the opposite direction, dying away as the capacitor discharges. Now let's move the plates further apart. If we now repeat the experiment, the same thing happens, but there is a difference. Watch. The current passes for a much shorter time. When the plates are further apart, we say that the capacitance is smaller. The battery pumps electrons round as before, but the plates can now hold less charge and the current stops flowing much sooner. Let's discharge the capacitor. Once again, current flows in the reverse direction, but again it very quickly dies away. You can see that the current must die away more quickly because there's less charge on the plates. They very quickly become neutral again. Watch it again in the lab. Now let's connect the battery permanently to the two plates of the capacitor. Current flows until the capacitor is fully charged. Suppose, once this has happened, we deliberately change the capacitance of the capacitor by moving one plate in and out. Then the charge on the plates will either build up as capacitance increases or be reduced when it decreases. We'll get current flowing in one direction or the other as the capacitance changes. We're changing static electricity into current electricity. Here's the capacitor again, with the plates very close together. It then has a high capacitance, as we saw earlier. When it's charging, the current passes for 2 or 3 seconds. And when we discharge it, again, a current flows for several seconds. There's another way in which its capacitance can be altered. Not by moving the plates further apart, but by making the area of overlap between them smaller, like this. It's as if the capacitor now has smaller plates. It now takes much less time to charge up. Its capacitance is smaller. And the current dies away as quickly when we discharge it. Capacitors are made whose plates can be moved relative to each other so that we have what's called a variable capacitor. This is one of a kind sometimes used in radio transmitters and receivers. You can see how the plates, there are several pairs combined in the one instrument, can be made to overlap to a greater or lesser extent by turning the knob. This makes the capacitance vary, and it's a way in which radio circuits are tuned. There are variable capacitors in radio sets, for instance. The tuning knob alters the capacitance, and the radio then picks up stations on different wavelengths.